Hello, chemistry fans, and welcome back to Chemistry 1032 problem solving session here at the Academic Success Center on Broward College North Campus. I am your host, Dr. Russell Betts, and I'll try to guide you through this problem today. Without any further ado, let's jump in. Chapter 10, Problem 6. Define the following terms: equilibrium and Le Chatelier's principle. Ooh, two really big concepts. These are huge. These are everywhere. These explain a lot in biology. These terms explain a lot in ecology. They explain a lot. They're very important terms. They're also extremely complicated. But I'm going to do my very best to simplify this for you. In 1032, we don't require you to know equilibrium at a very finite level. We just require you to have a kind of a 1,000-yard view of it. So let me give you an overview of what equilibrium means. First, let me state it. Equilibrium means the rate of the forward reaction in a system is equal to the rate of backward reaction. So now let's just draw a very simple idea. Let's draw a simple weak acid-base reaction. Let's have, again, our friend HF plus water is an equilibrium. Now this is an equilibrium arrow. So we have a half arrow to the right, half arrow to the left. Hydronium plus F minus. So this reaction is in what they call equilibrium. That means as the forward reaction goes, the backward reaction is also occurring at the same time. Okay? So as HF and water are reacting to give you hydronium and fluoride are reacting to give you HF and water. So the same reaction forward and the reaction backward in a flask are occurring at the same time. More importantly, they're occurring at the same rate. Now that's a little bit weird. The forward reaction is occurring at the same time as the backward reaction. So it's going this way at the same time it's going this way. Now, it's probably not the same molecules. It's probably not the same hydronium that's being formed that reacts back. Remember, there's probably, thousands of these molecules and thousands of these ions in the flask. So they find each other and they react this way. There's thousands of these and thousands of these. They react and go this way. So they're happening. It's going this way. It's going that way. It's going this way. It's going that way. It's going this way. It's going that way. At the same time. So at the same instance in time, both reactions are occurring. It's going to the right and it's going to the left. At the same time, at the same rate. Okay? That's called equilibrium. Now, if the reaction is going this way at the same time it's going that way, and at the same rate, so that means as fast as one molecule of this reacts to the right is as fast as this reaction is making a molecule of this. So nothing's changing. The concentration of the stuff on the right is not changing. The concentration of the stuff on the left is not changing. Because as fast as you're making products is as fast as you're making starting materials or reactants. That's equilibrium. You go to the right, make some products. The products say, nope, don't like it over here. They react together, form starting material or reactants. The reactants go, don't mind if I do. They react back to give you products. The products at the same time, at the same rate go, nope, I don't think so. Back to the left. Okay? It's occurring all the time. At the same time, at the same rate. As fast as you're making products is as fast as you're losing them. Okay? I know it's a little weird, but that's what equilibrium is. The rate of the formation of products is the same as the rate of the formation of reactants. The reaction is going back and forth. So, equilibrium. You make products, you make the reactants. You make the products, you make the reactants. At the same time, at the same rate. Okay? That means that the concentration of the starting materials and the concentration of the products doesn't change. They're just interchanging back and forth. They're just going back and forth. But the concentrations don't change. Now, Le Chatelier's principle says, if I try to mess with this equilibrium, if I mess with it, the equilibrium will shift one way or the other. Now that's a little weird. So let's just imagine then, I have my little pot of this reaction going back and forth happily. It'll do that for years and years and years until you mess with it. Okay? So let's say I walk by and I have a whole bunch of fluoride ions, and I say, I'm going to dump in a whole bunch of fluoride. So I dump in, say, 1 million molecules of fluoride. That's going to mess with the equilibrium big. Huge mess. Why? Because now I have a whole pot of fluoride ions that are finding the hydronium. Now this is a very, very abstract concept, so try to stay with me now. I'm in a system of equilibrium. I've tossed in a whole boatload of fluoride ions. So now the concentration of fluoride has gone way up because I've dumped a bunch in there. I've just said, oh, don't mind if I do, poured a bunch of fluoride ions into this flask. Now the concentration of fluoride has gone up. Huge. It's huge. Now, why does that make the equilibrium change? Because now there's more fluoride to collide with hydronium. Collide, don't forget, that's how reactions happen. Molecules or ions or whatever have to hit each other. In order to hit each other, they have to find each other. So if there's a lot more fluoride because I dumped a whole lot more in there, there's a whole lot more probability or chance that this fluoride ion will smack into hydronium because there's simply more of it. That will force the reaction this way to occur faster because there's more of this than there is of anything else. Okay? Strange concept, I know. So the Chatelier principle says, if you, shall I say, interfere with an equilibrium, say by adding more product, the equilibrium will shift this way. So let's say increase F minus. So if I increase F minus, let me just try to illustrate this here at the bottom. If I increase F minus, this equilibrium will shift to the left. And I drew a little arrow going to the right to indicate that the forward reaction keeps going no matter what. It's just now that there's so much HF, the equilibrium is shifting to the right to favor products. Okay? That's what I'm saying. Are you with me on that? If not, try to stay with me. I know it's complicated. I'm going to repeat the whole thing again. It is complicated. Okay, so if I increased F minus, there's a whole swamp full of these bad boys now, the F minus. When there's more of this than there was here, so going from here to here, I increased the concentration of F minus. I had literally added it. I just dumped it in the flask. Now the concentration of this is big, huge. The probability of smacking into hydronium goes way up because now there's simply more of it to collide. That will force the rate of reaction to go this way, it'll force the equilibrium to shift towards the starting materials or the reactants. Why? Because there's simply more of it to collide. That's the key. There's more concentration, more chances of collision, more chances of reaction. The rate of this backward reaction, if you will increase. Okay? Favoring equilibrium shifting this way. So the whole reaction will shift this way. Okay? Now, I know this is a very, very difficult concept, so let's go over the whole thing again. This reaction is in equilibrium. I have HF reacting with water to give me hydronium and fluoride. I have fluoride reacting with hydronium to give me HF and water. This is occurring at equilibrium. So what that means is the forward reaction and the backward reaction are happening at the same time, at the same rate. What does that mean? Well, that means as fast as this reaction is happening to give me my reactants is the same rate that the reactants are reacting to give me my products. And that will go back and forth forever, I suppose, until something happens, until somebody messes with the system. Now, how do we mess with the system? Well, one really good way is to increase the concentration of one of these or one of these. So I picked F minus because it was just the easiest one to pick. I could have picked hydronium. I could have also added more water. I could have also added more HF. If you increase the concentration of any one of these four things, it will shift the equilibrium in one direction or the other. I picked F minus. So if I swap this reaction with F minus, the equilibrium will shift to favor starting material or reactants. Okay? Now, I didn't have to increase F minus. I could have increased HF. If I increased HF, the reaction would have shifted this way, because now there's more HF to collide with more water to make more products. Okay? Try that again. If I increase F minus, the equilibrium shifts this way. So let's say I increase HF. The equilibrium now will shift the other way. There we go. If I increased HF, the equilibrium now is forced to go that way. Why? Because now there's simply more of this to react with the water to force the reaction to go that way. Okay? I know this is confusing. And I hope that this video has given you at least a little bit of an insight into how these two things work. If not, watch the video again. Maybe that'll help. Read it in your textbook. Your textbook gives a pretty good explanation of how this works. Raise your hand, find a tutor, have them help you understand equilibrium and Le Chatelier's principle. Go see your professor. Find us during office hours. We're more than willing to help you with this stuff. But you gotta kind of work for yourself a little bit on this. You can't just rely on us to come and find you. You gotta come and find us. Okay? Now, I used HF as my example. It doesn't have to be HF. It could be any molecule that's a weak acid or a weak electrolyte. It doesn't even have to be electrolytes. It could be pretty much any molecule can be in some kind of equilibrium. Equilibrium and Le Chatelier's principle explains a lot of physiology. It explains a lot of it. So it's important that you understand it. So please don't sit back on this. I'm imploring you to learn this stuff. Because once you understand equilibrium and Le Chatelier's principle, a lot of physiological processes make a lot more sense because of this chemistry. Okay? So please don't sit back on this. Please get help if you don't understand it. Now, with that, I want to end the video because I've said quite a bit right now. But I do hope that you find a tutor if you don't understand. Come find me during office hours or your professor. Get this stuff straight because it's very, very simple once you allow your brain to kind of wrap itself around it. Okay? Now, with that, I'd like to wish you good luck and good chemistry.